Herkese merhabalar. Tekrar DRP programına ayrıca hoş geldiniz. Biz de organizatörlere ayrıca teşekkür ediyoruz. Mentilere de ayrıca teşekkür ediyoruz. Bugün ilk konuşma Furkan Akal'ın konuşma başlığı Calculus on Manifolds with some Fundamental Theorems. Buyur Furkan.
Thank you. Hello, everyone. I'm Furkan Akal, and I'm a third-year physics and mathematics student at Middle East University, Turkey. Before starting my talk, I want to thank my mentor, Eyüp Yalçınkaya, for the great effort. And now let me start my presentation today. I will talk about calculus on manifolds. This is the overview of my talk. As you see, I've divided my talk into 3 parts. And let's start with the first part. In this part, we will discuss what manifolds are and give you some examples. Let me start with an informal introduction. Manifolds are some topological spaces which are locally homeomorphic to Rm basically, but it may be different from Rm globally, obviously. You can think of a curve and a surface as a 1- and 2-dimensional manifold respectively as an example of manifolds. If we wish to move on the formal definition now, here what we do is basically to express things that we've just informally introduced, just express those mathematically. This is literally what we did in the first 3 conditions, and the 4th condition gives us the differentiability or the smoothness of our manifold. And we call this UI phi I pair a chart and the whole family on an atlas, and we denote a coordinate as the set x mu of p. Now let's give a couple of examples if you wish. Rm is the most trivial example of a manifold because it can be covered by a single chart. You can take the homeomorphism as an identity map. It's an easy example. And next, let's give the second example as a 1-dimensional manifold. For m is equal to 1, only 2 different manifolds are possible. Those are the real line R and the circle S1. R is the trivial one, so let's try to analyze S1. In order to be concrete, let's take the circle with a radius 1 and in the xy plane. Let's define our charts. The mapping inverse pi is a map from the interval 0 to pi to S1 by this formula, and our second mapping inverse phi 2 is defined from minus pi to S1 by the same formula again. Note that the image of the first map is S1 minus the point 1, 0, and the image of the second mapping is the set S1 minus point comma 0 point. And hence we deduce that the circle S1 cannot be covered by only one of these charts. So we need 2 of them, and the rest is to verify that these mappings are homeomorphisms and that are the maps psi 1, 2 and the psi 2, 1 are smooth. After this introduction, we're ready to define other things of some geometrical objects or manifolds. For instance, a vector is defined to be a tangent vector to a curve in M, and this is very intuitive, right? After all, this is a very familiar idea to us from the first-year calculus. In single variable calculus, we have defined tangent lines to curves like this here. Now we're gonna generalize this idea basically. To do this in a more mathematical way, let's define a relation that relates 2 curves with these properties. And if these conditions are satisfied, then C1 and C2 yields the same differential operator at our point P. Note that this relation tilde is clearly an equivalence relation, so we can construct all the equivalence classes of curves at a point P or all the tangent vectors at a point P. And this forms a vector space called tangent space of M at a point P and denoted as TPM. At this point, obviously, E sub mu, which is equal to partial x mu, is the basis vector or are the basis vectors, while V mu's are the components of any vector V in our tangent space at P. Because TPM is a vector space, we have a dual space to TPM, and we will call it cotangent space. again at a point P, whose elements are linear functions or linear functions from Tpm to R. Informally, they each vectors and give us a real number. We call the elements those linear functionals or dual as dual vectors, or in the context of in our context, one forms. You can consider the differential of a function f, which is a zero form, by the way, as a simple example. If you want to define two forms in a similar way with the properties of bilinearity and the skew symmetry, observe that two forms defined from TPR3 cube or to R can be written in terms of one form with the help of the wedge product. Unfortunately, I'm not able to go in details of this wedge product or the other notions that I'm gonna express because of the restriction of the time. And in general, we can write them under a summation like this. Similarly, we can define M forms as well. Here we have a useful method to proceed the action of M forms to M number of vectors. And we can write the same summation, which we did for two forms right here for M forms as well, right here. And here we have an example for n equals 4, and we see a list of 1, 2, 3, and 4 forms for n is equal to 4. Okay, if we want to denote the vector space of R forms at any point in our manifold with capital omega, and we can write any element of omega in this form, and we will use it later, where we take those omega mu i's totally anti-symmetric. And the top of the slide, you see a proposition which comes from the non-commutativity of the wedge product operation. And now now we're ready to introduce the notion of exterior derivative. It is basically a function which takes an R form and yields an R plus 1 form with obeying this formula. Now, for an example, let's define the exterior derivative for functions or zero forms. This is very intuitive because we're very familiar with the differential concept from calculus courses. So this allows us to develop another formulation to exterior derivative in terms of differentials. If you wish, let's look at an example and see something concrete. Here we use a property that we haven't discussed yet to cancel here some terms, and it's here. The first one comes from the fact that again the commutativity of the wedge product, but the second one is the property that we used in the last example to cancel out some terms. And we have some classifications for K forms and like closeness and exactness. Note that since d squared is equal to 0 for any K form, exactness implies closeness. This is a good property. After defining derivatives on a manifold, let's continue with defining integration on a manifold. To be able to do this, let's start with defining some concepts. And let's start with M is equal to R to R to start with the basic one. To do this, we first define the standard R simplex and sigma as a P plus 1 cycle, R plus 1 cycle, where PI's are unit points in R to R. We can write it in a more proper way like this. And to see visually, we can see the visual examples. And this is how the standard 2 simplex and 3 simplex look like. Recall that how an R form omega on R to R is written in this form. We're going to use it. Then we define the integration of omega over sigma bar like this. It is easy to see that the right-hand side is the usual R-fold integration process. And for example, for R is equal to 2, we can easily calculate the integral and find the numerical solution, numerical result. If to be able to define the integration on other manifolds except R to R, the trivial one, we need to define some another concepts or notions, let's say. Here, the the like R chains and R boundaries are here. If sigma R is an R simplex in R to R, and if a function f from sigma R to M be a smooth map, then we denote the image of sigma R in M by SR and call it a singular R simplex in M. We call these simplices singular since they do not provide a triangulation of M. And next, if the set SRI is the set of R simplices in M, then we define an R chain in M by a sum of R simplices with real coefficients. And finally, those R chains in a manifold from the chain group C sub Rm. With the help of these concepts that we just defined, we can define an integration of an R form over an R chain in our manifold, any manifold M. So we use this equation. This is the pullback function, if you're familiar with. When we apply the pullback function, then we have again the usual R-fold integration at the right-hand side of our integral equation. And so then rest is just to evaluate it. And this is the part that I love so much. This is the Stokes theorem, very beautiful theorem, I must say. Most of you probably are familiar with in the context of vector calculus on R3, but this is the generalized version of it. I would love to prove it step by step here, but unfortunately, I don't have enough time again. I'm really sorry about that. On the other hand, if there is anyone who is interested, can easily check it from any calculus on manifold book. In R3, one can write the Stokes theorem in this form, which is probably the one that most of you are much more familiar with. And so far, we tried to emphasize some abstract notions in calculus on manifolds. Now, let's try to relate the things that we covered so far with some notions in the vector calculus on R3. And since one form on U is a kind of linear combination with function coefficients of dx, dy, and dz, we can identify one forms with vector fields. In a similar way, we may identify two forms with vector fields again, and three forms can be identified with functions on a subset U. After these identifications, we may try to relate the operations as well. Let's try to take exterior derivatives of these forms and see what they will correspond to in the vector calculus manner. First of all, the exterior derivative of a zero form f can be identified with the gradient of f in the vector calculus. Similarly, the exterior derivative of a one form corresponds to curl of a vector field, and it yields another vector field clearly. Finally, the exterior derivative of a two form corresponds to the divergence of a vector field and gives us a scalar or a function, let's say, instead of saying scalar. The following, and yeah, this diagram tells very well what I tried to emphasize, and you can easily see the isomorphisms between the sets of forms and smooth functions and vector fields, and the relation between the exterior derivative operation and the other vector fields, vector calculus operations. Here, let's remember some important propositions from the vector calculus on R3. Now we're about to relate these with some properties in the context of differential forms and exterior derivatives. One can easily see that the first two propositions express the property of exactness, and the last proposition expresses the fact that exactness implies closeness, because we identified all these operations with just an exterior derivative operation, and both of these give us this equated equal to zero property, and this is the property that exactness implies closeness. I'll just briefly talk about the manifold and calculus on manifolds so far. In the final part, I want to discuss the notion of curvature briefly and propose another beautiful theorem at the end. Let's start with remembering the concept of metric and metric tensor. In this context, our aim is to figure out how to calculate distances on different manifolds. Recall that how we calculate the distances via inner products. For instance, in rectangular coordinates, we have obviously the identity as a metric tensor. On the other hand, our metric tensor is different, which is caused by the change of basis operation in the polar coordinates example. Here, before introducing the curvature notion or the Riemann curvature tensor, we need to cover the Christoffel symbols. As you see, there are two types of them. This is the first kind of Christoffel symbol, and this is the second kind. And we can, this is the second kind, and we can easily obtain the second kind from the first kind via the tensor index lowering process. And these are to calculate the query curvature of a manifold, we need the Riemann tensor, and we don't have to. And here again, two different types of Riemann tensor. This is the second kind, and this is the first kind. And again, we obtain the one from the another with a lowering index process in tensors. To calculate the curvature of a manifold, we don't have to calculate all the components one by one. Using these symmetry properties makes our calculations easier. For instance, if you have Rijkl, then you have Rjikl as well. And the other stuff are as much as useful as well. Now we can talk about the Riemannian curvature relative to a given metric. We need three things to proceed this. Those are a point on our manifold and two different vectors. Using this, we can compute the curvature on a manifold relative to a metric. In an informal expression, we say that we use those we use those two vectors and that point, and obviously these vectors are elements of the tangent space at that point. We just measuring how much the surface are different from the flatness in terms of curvature. This is the informal expression, obviously, but the mathematics here. I would love to make an example and calculate the curvature of a trivial manifold, but it's really long business, and it's full of nonsensical computations. You have to calculate the Christoffel symbols with the help of partial derivatives, and you need to calculate a Riemannian tensor with use the Christoffel symbols that you obtained at the last part, and finally you find the curvature. Note that one can verify that the curvature corresponding to a Euclidean metric is 0.
Furkan, by the way, 3 minutes left.
Okay, thank you. Lastly, I want to talk about the Gauss-Bonnet theorem. This is a very beautiful one, by the way. Before that, let's remember the Euler characteristic. It is defined for the surfaces of polyhedra according to the formula. Here, chi is equal to the number of vertices minus number of edges plus number of faces. And it is equal to 2 for any convex polyhedron surface. As an example, we can look the sphere. This triangulation gives us 6 vertices, 12 edges, and 8 faces. So we can easily see that Euler characteristics would be equal to 2 for this example. And this is the statement of the theorem. Here we're working on a two-dimensional compact Riemannian manifold with boundary del M. Here the K be the Gaussian curvature, and let Kg the geodesic curvature. But since we're trying to emphasize something much more intuitively, let's introduce another formulation for boundaryless two-dimensional Riemannian compact manifolds. As an easiest example, we can consider the sphere. Personally, the reason why I love this theorem is that while left-hand side of the equation is geometry and the right-hand side of the equation is topology. Here we have a curvature of a manifold, and here we have Euler characteristic, which is a topological notion. So this theorem unifies a geometrical concept and a topological concept, which are my favorite field of mathematics. And this is the end of my talk. Today, I've tried to cover the manifold concept, calculus on manifolds, namely derivatives and integrations, and finally, the notion of curvature. I'm very thankful for you to listen to me with a great passion. If you have any question, I would be glad to answer. Thank you.
Teşekkürler Furkan konuşma için. Teşekkür ediyoruz. Biz de